This is 2012, number 6. So they want you to find the total distance as opposed to displacement. And so we have to know if the velocity is ever negative, if it's positive, what regions. So to do that, you kind of have to have an idea of what that looks like. And knowing what t-squares look like, they are parabolas. This is a parabola. The negative in front makes it upside down. So we know it's an upside down parabola. And then the other thing we can do is factor this. So if I take a t out, I'll get 6 minus t and set that equal to 0. I get 2 y-intercepts, 0 and 6. So what does that tell me, and why is that important? Well, if I cross at 0 and 6 and it's upside down, the graph's going to look like that. And why does that matter? Because when I want to find total distance, when I integrate, does not find total distance. Integration finds displacement, change in position. But since the velocity is always positive, it's always moving to the right, so the displacement and total distance are the same. I don't have to worry about it. So let me show you. You would integrate the velocity from 0 to 3, and that will give you, in this case, the total distance and displacement, and I'll just kind of remind you why. So the antiderivative of velocity is position. I will explain that. So let me replace velocity with 6t minus t squared. Now I take the antiderivative of that. It's going to be 6t squared over 2 minus t cubed over 3. And that's from 0 to 3. And that simplifies to 3t squared minus t cubed over 3. That's from 0 to 3. And then I plug in 3. So it's going to be 3 times 3 squared minus 3 cubed over 3 minus, and then if you plug in 0, you're just going to get 0 for everything. So we'll have that. And then the first part's 27, and the second part's going to be 9. And then I get 18, D for my answer. So let me clarify a little bit about total distance and displacement and why this works. So let me show you what's going on. Velocity is the derivative of the position function. So in essence, this is this. The antiderivative of x prime is just x. So what is this really saying? This is the final position of the object. This is where it started. So this gives you the change in its position. So when you integrate velocity, it gives you change in position, which is also known as displacement. Now, if you look from 0 to 3, it's always moving to the right. So the final position minus the starting position is also the total distance it's going to travel. But what if we went to a further point like 9? Here's what's going to happen. All of this is going to be negative because you're doing a net area when you integrate. And all of this is going to be positive. I'm going to make up some numbers. They're not even going to be, I don't think they're even close to right. But suppose the area of this was 5 and the area down below here was 2. So total distance obviously would be 7 because you went a total of 5 one way and then 2 the other. But if you actually integrated this, it would be 5 minus 2 and you get an answer of 3. So again, important to understand why 3 as opposed to 7. If this is 0, this says you move 5 to the right. So the object moved 5 to the right. And what does this say? Since the velocity is negative here, that means you're moving to the left, and you move 2 to the left. And so what's your final position? Because this gives you change in position. Your final position compared to your original is going to be 3 because you went 5 right, 2 left. So your displacement or change of position is 3. But if you want the total distance of this case, you'd have to add how far you went right and how far you went left. I went total 5 plus 2, I went 7. So be careful about knowing displacement versus total distance. If you want total distance, you have to absolute value your velocity. But in this case, we didn't because it's always positive on our domain. So that is a long explanation of that problem.